Okay, so we're entering a new unit on circles. So starting off today, looking at circle vocabulary and some basic relationships. So first off, we're just defining what a circle is. It's the set of all points that are equidistant to the center. So my center here is point L, and I'm looking at the set of points that are equidistant, so anything around here, from that fixed point, that center. And that distance is, of course, we're talking about what the radius is, because any radius will be congruent to any other radius in the same circle. So when we name a circle, we name it by the center. I use a circle notation, little circle, little dot inside, and then I point out the center right here. So we would name this as circle L, right? L right here is the center, and these are, of course, all of those points on the circle that are the same distance from that center. Okay, if we talk about a chord is a segment with endpoints on the circle. So if I look at my picture right here, from C to L, that is a segment that has endpoints on the circle, here to here. So we could call that segment CI, for example. Segment notation, put that little dash above it. Okay, our diameter here is also a chord. So we start by saying it's a type of chord, a segment with endpoints on the circle, but it's the longest chord that we can draw inside of any circle because it passes through the center. So if I look at a chord that passes through the center, that must be this segment right here from A to I because it passes through point L. So it's the longest chord that we can draw inside of any circle. It splits our circle perfectly into two congruent half circles. All right, so my example here is AI. Now, of course, with segment notation, we could have reversed the order. That would be fine. So if I wanted to call this segment IA, that is the same segment. That's the same diameter. Okay, next, radius. Radius is a segment that connects the center to the circle. So if this is my center right here, this would be a radius. This would be a radius. This would be a radius. And again, any radius inside of my diagram, inside of any circle, has to match any other radius in the same circle. So here, for my example, I'll say this one, LB. And then a little reminder here that the radii, plural for radius, right, they have to be congruent. So if I knew that this measure here was 10 units, this would be 10 units, this would be 10 units as well, right? The distance from my center to any point on the circle, anywhere, right, must be 10 units. All right, next we're looking at our different angles. So for angles here, let me kind of chunk those together. We have our central angles first. So a central angle is an angle with its center as its vertex. So if I'm looking at, here's my center of the circle, I could be talking about this angle right here, for example. This would be a central angle. L right here is the vertex of that angle. So I can name that angle ALB. I could also call it BLA, that's fine. But when I put that vertex in the middle, right here, right, I just have to make sure that it reads as ALB or BLA, that the vertex right there is the center of my circle. Okay, an inscribed angle, inscribed inside, is an angle that is inside of the circle that has its vertex on the circle. So if I look in my model right here, the only angle I have right here that has its vertex on the circle is this one. So this angle right here is an inscribed angle, right? Its vertex right here is really, it's an angle that's inside the circle. Vertex is on the circle right here. So inscribed, angle is inside, vertex is on the circle. So I can name this AIC or CIA would be fine as well. I'll say it the first way I said it. AIC. Okay, next looking at our different types of arcs. So I'm going to chunk these three together right here. All right, so a minor arc is an arc that is less than half of the circle, so less than 180 degrees. So if I look at my model, I could say, well, this one right here, B to A would be a minor arc. It's less than half the circle. I could say A to C, that's a minor arc. It's less than half the circle. C to I, right, that's a minor arc. It's less than half the circle. All of those would work. We just have to change our notation. So B to A, for example, so if I'm trying to say B to A, I got to put this little curve over it to make sure that we read it as an arc and not a segment. Okay, next we have a major arc, so an arc that is more than half of the circle, so more than 180, but less than 360 degrees. So let's say that I'm trying to capture this arc here from A past C, past I, all the way to B, right? So if I'm trying to say I want this arc in this direction, not this small one, I need a different notation, because if I say AB or BA, I think it's the minor arc. So here I use a three-letter notation. I have the two endpoints, and then I just pick a point that falls in between. So for example, I can name the major arc ACB, that would be fine, or AIB, that would be fine as well. I'll do AIB. So again, an arc that is more than half the circle, we use a three-letter notation. So the two endpoints and a point that falls in between. Okay, a semicircle is an arc that's exactly half the circle. So the endpoints really are endpoints of a diameter. The measure is exactly 180. So here, if I look at this diameter right here, again, if I said arc AI, which arc are we talking about? Are we talking about this arc from A to I, or this arc here from A to I? So to be super clear, we need to make sure that we use a letter in between, a point that falls in between. So if I want this arc over here, I could say ABI, or this one here, I could say ACI. I'll do the first one that I said. So ABI. So again, for these two, right, for our major arcs and our semicircles, we need to name it by the two endpoints with one point in between. Okay, so lastly, we have our two types of lines. Let me get out a little bit. Okay, slide it up a smidge. So our two types of lines here. So we have tangent, we have secant. So a tangent line is a line that has one point of intersection with the circle. So here in my diagram, I have two lines. I see I have this line here and I have this line here. So my tangent line is this one right here because the point where it touches the circle is right here at B. We actually call that the point of tangency. It's the location where it makes contact with the circle. So this right here is my tangent line. I can name a line using any 2 points on the line with a double arrow on top. So I'll say TB with a little double arrow on top, like that. Okay. And then lastly, imagine that we have that point here, right? Points there and there. So TB, BP, PB, right? Any of those would be fine. All right, lastly, we're looking at the secant line. So a line that has 2 points of intersection with the line. So the only line that I have right here that makes 2 points of contact is line CI or IC, right? Either way is fine. I'll say IC. Okay, so a tangent line has 1 point of contact with the circle. That is the point of tangency right here. And a secant line has 2 points of intersection with the circle. This is the secant line right here. All right, let me slide up. Next, we're just doing a little review of what we've covered earlier this semester. Let me get back in it just a little bit tighter. All right, so a little review, right? We've already talked about this when we talked about shaded region problems. So we know that pi, right? Pi is about 3.14. Pi is really the ratio of a circle's circumference, right? The total distance around a circle, divided by the diameter, the longest distance that we can draw connecting one point on the circle to the other, passing through the center of the circle. So pi is the ratio of circumference to diameter. Okay, and then the circumference of a circle would just be pi times diameter, or 2 pi r, because we know that a diameter is 2 times the radius. Okay, area of a circle is pi r squared. Okay, over here, a reminder of how we get to a sector. So it's this little shaded region right here. It's like a slice of pie. The way that we get there is the ratio of the sector to the circle. And then we multiply that by the total area. So our sector is really a portion of the total area. So imagine that this was a 45-degree angle. Right, it'd be 45 degrees over 360, so that would be 1/8 times whatever the area is, right? We'd want 1/8 of the total area. To get to this little segment right here, we find the area of the sector first, and then we remove that hollow triangle. All right, we've seen this before, so this should be just a little recap, a little review. Okay, at the bottom, a few other relationships to consider. So first is, how does a central angle relate to its intercepted arc? So my central angle is right here, right? It would be this angle ABC. B would be the center of my circle. And then the intercepted arc is just the arc that's in between the rays of that central angle right there. So here, this one is pretty clear cut. Our central angle, whatever that measure is, it's always the same as the measure of the intercepted arc. So central angle, same measure as the intercepted arc. So if this was, say, 70 degrees, this would be 70 degrees. If this arc was, I don't know, 85 degrees, this angle would be 85 degrees. They're always going to be the same when it's a central angle. Again, the vertex right here is the center of the circle. Okay, next one, also pretty intuitive. So arcs of congruent chords are congruent. So here I have this chord is congruent to this chord. We see the tick marks. So that means that this arc from here to here would have to be the same measure as this arc from here to here. Right? Really, we can just think of it as we are cutting off equal portions of the circle. Okay, two more relationships, and then we'll go to the flip side. So if I want the arc length, so I want this measure from here to here, right? B is the center of my circle. This is a central angle. So really what I'm looking for here is a portion of the circumference. Let me write that. So portion of the total distance around the circle, a portion of the circumference. So it's really similar to how we get our sector, right? Here we're going to think L is our length. We're looking at the degree measure of our central angle will be the same as the degree measure of our intercepted arc right here. We divide it by 360, and then we multiply that by the circumference, which is 2 pi r. So if I'm looking for the length of this arc in units, right, it's really just a portion of the circumference. So I need the ratio of my arc to the whole circle, so whatever that measure is to 360, and then multiply by circumference. Okay, and then lastly, well, what if I know the length and I want to express it in degree measures? So imagine that I want the same thing. I want this, but I want it in terms of degrees. So here, let's say we start off with that same intuitive formula. Length equals the degree measure of the arc to 360, right? We don't know that value. And then times the circumference 2 pi r. So let's use a little bit of algebra to get that m by itself. So first thing that we would do is we'd clear our fraction, right? We multiply each side by 360. So here this cancels away. So now we have 360 times the length, right? Again, 360 degrees times the length equals the degree measure times 2 pi r, the circumference. So if I want my degree measure by itself, I just divide out the circumference, the 2 pi r from both sides. So here the 2's cancel, the pi's cancel, the r's cancel, and we have the m all by itself. So the arc measure in degrees ends up being 360 degrees times the length divided by the circumference. Now, if you're plugging this into your calculator, though, you want to make sure that you're preserving the order of operations. You want to make sure that you put parentheses around the denominator so we view it as its own package. Okay. All right, we're good on this side. Let's flip it to the back. Okay, in class, I would typically have you guys pause and have you practice example 1. So if you have that ability now, I would say just pause the video and see if you know each of these terms. So I'm giving you the proper notation, and then I want you to name each of these figures. Okay, and I'm just going to roll into it. So I would say pause. Why don't you try it yourself? And now I'm just going to go over it. All right, so BDE. I'm using a 3-letter notation. My endpoints must be B and E here, and I'm saying BDE. So it looks like these are endpoints of a diameter, right? G is the center of my circle. So right here, that must be a semicircle. Okay, next, a 2-letter notation, and it's an arc. We're saying B to F here. That looks like a minor arc. It's less than half of the circle. Okay, FE, I see the little arrows, right? So that tells me that it's a line. So here's F and E. I have 2 points of intersection here. So that tells me it must be a secant line. Okay, 3-letter notation, and it's an arc. D and E are the endpoints. So D and E are the endpoints. Must pass over F. So I'm reading it from here all the way over to here. Okay, more than half of the circle. That must be a major arc. Okay, now an angle. Angle BEF. E must be the vertex of it. Here's the E right here. So we're saying BEF. So that vertex here is on the circle. The angle is inside of the circle. So we're calling that an inscribed angle. Okay, segment EB. So EB, those are endpoints on the circle. It passes through the center. So that would be not just a chord, that would be more specifically the diameter. But remember that your diameters are always also chords. Okay, another line. So CB, so 2 points that are on the line. So CB here and here. We see that we have 1 point of contact right there where B is. We would call that our point of tangency. So this line right here, that 1 point of contact, makes it a tangent line. Okay, another segment, BG. So here, B to G. G is the center of my circle. That makes it a radius. Okay, good time to remind you that any radius, so BG, GD, GE, right, they're going to be congruent to any other radius inside of the same diagram. Okay, another angle, angle DGE. DGE. G again is the center of the circle. So that is a central angle. Okay, last segment, EF. So EF, right, it's segment notation. So I'm reading it from here to here. So I have endpoints on my circle. That would be just a chord. All right, we should be good with notation and vocabulary. And whenever we name a circle like this, we're saying that G is the center of that circle. All right, next up. Find the measure of each angle or arc in circle X. So if I call it X, X is the center of the circle. Now in this one, I don't have any segment that's building off of a center. All I see is that I have 6 congruent chords, or I could visualize that as an inscribed regular hexagon inside of my circle. What I notice though is that with those 6 congruent chords, they all cut off the same portion of the circle. And if a whole circle is 360, I could split it 6 ways and see that each of those minor arcs here, 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 all the way around have to be 60 degrees. So I'm going to go ahead and add that to my picture. Okay, and then answer what I'm asked for to the right. So I want the measure of arc FO. So here are the 2 endpoints there, F to O. It's a minor arc, 2-letter notation. So 60 degrees. TER, so T and R are the endpoints passing over E as we connect T to R. So that looks like half of a circle, right? That is 180 degrees. That's actually a semicircle, exactly half of the circle. TOE, so here's T to E, must be passing over O to connect. So I have 4 arcs that are all 60 degrees, so 240 degrees total. Okay, on to the next one. All right, so in this one, X is the center. So I have all of these central angles that have measures the same as their intercepted arcs. So this arc must be 35, this one's 48, this one's 118. Now I see that these chords are congruent, so their arcs must be congruent. So I must have a 48 here, which means a 48 here also. Okay, my missing angle and my missing arc must be the same degree measure, and collectively, right, all of them have to add to 360. So if I take 360 and I subtract the 35, 48, 48, and 118, I'm left with 111 for my central angle here and its intercepted arc. So I'd go ahead and fill in that missing gap first. Now I'm asking for arc QR. So here to here, the minor arc, 48 degrees. Okay, T to R, so T to R, here to here. Again, the shorter pathway because it's two points right there. So if I add up the 35, the 48, and the 48, I get 131 degrees. Here I'm saying PSQ. So P and Q are the endpoints, and I'm going the long path that connects them. So I could add up all of these measures, right? That would be fine. But probably easiest if I take 360 and subtract that 48, right? That would get me a little bit faster to my conclusion of 312 degrees. Okay, lastly, TPS. So T and S are the 2 endpoints, and we're reading it so that we pass over P, so this direction. So I'd probably use the same strategy. I'd take my 360 and subtract the 111, I'd get there faster, 249. So in all of these, we just have to remember that a central angle is going to have the same measure as an intercepted arc, and a 2-letter notation means minor arc, semicircles, and major arcs use a 3-letter notation, the 2 endpoints and a point that falls in between. All right, next, find the length of the minor arc in units. Leave answer in terms of pi. So remember that we're solving for a length. Our length is a portion of the circumference. So my length is going to be whatever the degree measure is to 360 times the circumference of 2 pi r. So I'm looking at 60 to 360, right? That's going to tell me that my arc is 1/6 of the circle if I reduce it, times 2 times pi times 12. So I need 1/6 of 24 pi. And remember, it's length that's over 1. So if I multiply this through, that's really 24 pi over 6. And that cleans up nicely to be just 4 pi. So 4 pi units. I'll just leave a sweet little U for units right there. Okay, and then I'm saying, well, what if I want the degree measure of the arc? I want this measure in degrees. I know its length, right? So this is the length right here, and this right here is obviously the radius. Okay, so my degree measure, we just derived it, right? We solved this formula for m. So the degree measure is 360 times the length divided by the circumference. And don't forget that that bottom here needs to be in parentheses to preserve the order of operations. So I'm typing in 360 times 19.63 divided by 2 times pi times 25, all in parentheses. All right, and I've said you can type in for pi, round to the nearest hundredth, so 2 decimal spots. I've already told my calculator round to the nearest 2 decimal spots. So 360 times 19.63 divided by, in parentheses, 2 times pi times 25, close parentheses. All right, so here we end up with 44.99 degrees. Okay, next up, a little bit more review, right? We already talked about some circles in shaded regions in the beginning of the semester, so we're circling them back. So first, can you go forwards and backwards from area to circumference, circumference to area? So can you find the area if we know circumference? So if we know circumference, that's 2 pi r. We want area, that's pi r squared. So what they share in common is the radius. I need to figure out what's my radius. So I know that 2 pi r equals 64 pi, right? That is my circumference. So if I divide each side by 2 pi, I get my radius is 32 units. So that's what I'm plugging in for area. I need to square 32 and slap on the pi. So I end up with 1024 pi. Area is always units squared. Okay, if I go the other direction, if we start with area, can we figure out circumference? So area again is pi r squared. We want circumference 2 pi r, right? So I need to figure out my radius. So pi r squared equals 64 pi. Divide out the pi. Radius squared equals 64. Take the square root of each side. Algebraically, radius will be plus or minus 8, but obviously radius has to be just the positive. Can't have a negative radius measure. So 2 times 8 gets us 16 pi, and then U for units. All right, last 2 review problems, sector and segment, and I'm saying leave in terms of pi. All right, so the area of the sector, so my area of the sector is the degree measure of the sector to the circle times the area, pi r squared. So here the degree measure, I'm going to give you that little box notation, means it's 90 degrees to 360, right? So it's a quarter of the circle that is shaded. That's my slice of pi. Times pi times 6 squared. So I need 1/4 of 36 pi. Again, picture that as a fraction. 36 over 4 gets us 9 pi. So my sector has an area of 9 pi square units, right? It's 1/4 of the total area, which would have been 36 pi. Okay, lastly, can you find the area of the segment? So remember here that we're looking at the sector minus the triangle. And this triangle here has to be isosceles. That's a radius, so that has to be 6 also. These two base angles have to be the same. So if we split the remaining 120, I have a 60° here and here, which means that this particular triangle is also equilateral. All of the sides are 6, all of the interior angles are 60. So first I'm working on the sector. So I know it's 60° to 360, right? So it's like 1/6 of the circle times pi times 6 squared. So 36 pi. Again, put it over 1, right? And 36 over 6 is just 6. So the sector has an area of 6 pi. If this whole piece was shaded, that would be 6 pi. Okay, and then the triangle, let's say that I draw it out a little bigger, right? It's equilateral, so if I split it down the middle, it splits into 2 congruent 30, 60, 90 triangles. Each side is 6, so each half side is 3. I'm going to need the height of it. So if this is x, this is my x root 3, 3 root 3. So half base times height, half of 6 times 3 root 3. Half of 6 is 3 times 3 is 9. So 9 root 3. I take my sector, I subtract my triangle, and I have my segment. So 6 pi minus 9 root 3, units are squared. All right, so moved us forward in terms of circle vocab, circle relationship with a little bit of review as well. Have a good day.